Consider the function p of z given here, defined over the complex numbers. Show that z minus 2i is a factor. Well, if it is, we know that p of 2i would be equal to 0. So that's going to give me 2i to the power 4, take away twice 2i cubed, plus 14 2i squared, take away 8 lots of 2i, add 40. Well, I to the 4 is just 1, so this is 2 to the 4, which is 16. I cubed is negative I, so that's going to make that a plus. 2 cubed is 8 times 2 is 16, so we'll have 16i there. I squared, of course, is negative 1, so altogether this is negative 4. Negative 4 times 14, so that's going to give me negative 56. And here I've got minus 16i and plus 40, and we can see that that comes to 0. So hence or otherwise, we want to solve this equation giving solutions in the form a plus bi. Well, if z minus 2i is a factor, we know that z plus 2i must also be a factor. So this gives me z squared, take away 4i squared, which is plus 4, is also a factor. Now, z to the 4 minus 2z cubed plus 14z squared minus 8z plus 40 is equal to z squared plus 4. Open a bracket. We must start here with a z squared to get the z to the 4 here. We must finish with a plus 10 in order to get the plus 40 here. And we don't know what the middle is. But what we can do now is look at, say, z cubed coefficients. Now on the left here it's negative 2. Over here I'd get az cubed, and that's the only one that gives me a cube. So a is negative 2. So I now know that it factorizes to z squared plus 4, z squared minus 2z plus 10. So to find other solutions, I need to solve z squared minus 2z plus 10 is equal to 0. So we could use the quadratic formula here, or I'm actually going to do this by completing the square. Z minus 1 all squared, take away 1, add 10 is equal to 0. So z minus 1 all squared is equal to negative 9. So that tells me that z minus 1 is equal to plus or minus 3i, and therefore z is equal to 1 plus or minus 3i. So all of our solutions are 2i, negative 2i, and 1 plus or minus 3i.